Hello guys, welcome back. This is our second video on gas mixtures, and in this video we're going to solve a couple of problems showing the table approach to analyze mixtures. If you are unfamiliar with this, please refer to our first video, and if not, let's get started. So in this first problem, we have gas mixture. In this problem, we have a gas mixture that consists and 1 kilomole of helium, 2 kilomole of oxygen, 0.1 kilomole of water, and 1.5 kilomoles of nitrogen. We will need to find out the composition on mass basis and the average molecular weight and the gas constant. First of all, notice that this is a molar analysis. So according to our procedure, the first thing that we need to do is to list the components. So we have helium, we have O2, we have water, and we have nitrogen. And then the molecular weight of each one. For helium, we know the atomic is 2, so this will be next. We have our the data that we have. This is the number of moles that we have. These are in kilomoles. So we're just gonna copy the information that we have. We add them all together, we'll only see that we have 4.6 kilomoles of substance. We can compute the molar fraction. This is adimensional. I remember that the molar fraction is the individual number of moles divided by the number of moles of the mixture. So for the helium, it will be 1 over 0.46. This number is 0.2174. It's a dimensional since it's a ratio, and we do the same. If we do it correctly, the summation should be 1. Sometimes what it is not is caused by rounding errors. So now, we would like to get the total mass of each of the components. In order to do that, we start by using the molecular weight. Remember that this is mass over the number of moles, but the unknown is mass, so we're going to get it the number of moles times the molecular weight. So we can get the mass of each of the components, and this of course will be in kilograms. The first one, we have 1 mole times 2. This is 2 kilograms. If we add all of this, we're going to have 111.8 kilograms. This number is the number of moles of the mixture. This is the total mass of the mixture. So we can get the molecular weight of the mixture as finally, for the gas constant, we studied that the gas constant will be the universal gas constant divided by the molecular weight. Okay, as we talk about, if we use our ideal gas model, this will be the gas constant for this mixture. So we have find the composition on mass basis here, the average molecular weight, and the gas constant. So this is for our first problem. In this case, we have a mixture that consists of 30% of oxygen, 10% of CO2, and 30% of methane. The difference here is that this percentage of the percentage of this mixture is given by volume, and but in this case we don't have the total number of moles, we just have the volume, and we said that by volume means that this is the mass fraction, the molar fraction. And at this point of time, we're going to use it as a true, and we're going to find out why this is true in the next video. So we're going to start with the same approach. We say the component. We're going to add the molecular weight. Now, we don't have the total number of moles. So what we're going to do is we're going to assume a number of moles. That is the total number of moles of mixture. For simplicity, we're going to assume that we have 100 moles. And this helps because if this number that we have is the composition, we know that this is 30. It doesn't matter the number that we choose here. If we choose 11, if we choose 10, if we choose 16.5, will be the same. It will make just a little bit harder the multiplication that we need to convert from here to here. Okay. With this in mind and following the same procedure we did last time, that means that we're going to use the molecular weight as the mass divided by the number of moles. So the mass in this case will be the molecular weight times the number of moles. So for oxygen, we can repeat this so we can compute our molecular weight. And our gas constant, this is of the mixture. As an exercise, and in order to confirm that these two numbers will not change, try with total number of moles of 250. In that case, if, just for your reference, if the number you have of 250, that means that the number of moles for CO2 should be the 10% of this, that will be 25, right? So try it. Before we finish, let's say that we have a real-world application. This machine is called the ORSAT analyzer, and this was used to analyze flue gases, that means exhaust gases for combustion. And in each one of these, we have different substances. We have potassium hydroxide here, alkaline pyrogelic acid, and ammoniacal compost chloride. So in this first one, we are having a mixture that has CO2 plus O2 plus CO plus a bunch of things. When this apparatus was invented in the 19th century, we would like to capture CO2, O2, and CO. This is the basic analysis that we find out now in our verification. You can see that we have same things, except that we now we check the onboard fuel and the nitrous oxides. Um, so this is something that we still use today, and this is a gas mixture that give us a great headaches. Okay, guys, this is all for these videos. Thank you. Next video, we're gonna show how to analyze properties for gas mixtures. Thank you.